Hi everyone, I'm Liz Cutlip and I'm going to be talking to you today about interactions between 2D halide perovskite materials and methylamine or MA vapor. There's a lot of excitement around this topic because perovskites have the potential to surpass the efficiency of silicon solar cells, and because they offer the opportunity for some unique types of solar harvesting. We are interested in the structural tunability of halide perovskites, especially the 2D Ruddlesden-Popper phases, for two main reasons. One being that the addition of a 2D perovskite phase can reduce moisture sensitivity and improve solar cell stability. The second reason being is that it potentially offers beneficial improvements in the design of color switchable photovoltaic windows. Perovskites have the capability of switching from their colored light absorbing active phase to various different structural phases where they are visibly transparent. You can see this in the image at the bottom left of the poster. While there are other possible color changing mechanisms, the structural change shown here and throughout our work occurs because of MA gas intercalation. This color-changing property is what sparked the idea of color-switchable solar windows, which was pioneered by Lance Wheeler and others at NREL. From their proof-of-concept work, we saw that multiple color changes through intercalation and deintercalation of MA gas caused the perovskite power production to degrade rather quickly, which you can see in the schematic below the image from before. We believe that this degradation is a result of morphological changes due to color cycling. This degradation prompted us to explore the stability of perovskite materials when exposed to MA gas. To begin, we looked at ways of stabilizing perovskite films and devices in other applications. As mentioned before, one promising approach uses a mixed system of standard 3D perovskites and 2D Ruddlesden-Popper phase perovskites to increase stability in these morphological changes, which is what drove the degradation process from before. You can see these positive effects of this method in the data from the Snaith groups shown here in the top right of the poster. This promising data led to our work in the interactions between 2D perovskites and methylamine gas. By studying these interactions, our goal was to better understand the effect of the organic spacer molecule in these materials right up here and its interactions with the lead halide sheets. Ultimately, our goal is to better understand these interactions to improve the design of 2D, 3D perovskite materials. Experimentally, we have so far tested 3 different 2D spacer molecules, as I mentioned before, EA, PEA, and 4-fluoryl PEA. This was done by exposing the 2D perovskite thin films to MA vapor to change their color. We then analyzed changes using absorbance and X-ray diffraction after methylamine had been removed. Some key findings within these experiments were that the exposure to MA gas caused PEA and 4-fluoryl PEA to form a mixed 2D, 3D perovskite phase. You can most clearly see this in the absorption data right here. What we see in this data is that following MA deintercalation, some of the methylamine still remains within the film. We see that as a change from a pure 2D perovskite where the lead halide sheets are 1 layer thick, N equals 1, to when the gas goes through a color switch, we get 2 layers of this perovskite sheet, N equals 2, with MA remaining within the structure. Another interesting result is that there is evidence of a switch to this traditional 3D perovskite phase when EA organic spacer was used, which you can see in this absorption data here. Then, with further MA exposure, we see a large blue shift in absorption, which may be due to the formation of 1D materials. There's still work to be done to better characterize exactly what is happening with EA, but there are clearly some interesting things going on there which we are going to look at further. What we've learned so far is that we think MA intercalation can give insight into behavior of 2D perovskites. It also yields insight into the structure of a mixed 2D, 3D perovskite. We have done some baseline testing of these materials for color switchable solar cells, and we are seeing some promising results, although much work is still needed. In the future, we hope to further our research in the A-site cations in order to further improve design rules for mixed 2D, 3D halide perovskites. Hopefully one day we will see color switchable solar cells on the market. I'd like to acknowledge my advisor, Dr. Christians, the Hope College Dean of Natural and Applied Sciences, and the Claire Booth Luce Research Scholar Program of the Henry Luce Foundation. Thanks for tuning in today, and if you have any questions, please feel free to email us.